Hello everyone, I'm Zhang, a PhD candidate in the UC Riverside. Welcome to the presentation of the Bi-directional log structure MergeTree. It was finished by our group, the Big Data Lab in the UC Riverside. Here is the outline of the whole presentation. Let me first quickly introduce what is the log structure MergeTree. Everybody knows B-tree. It's a traditional database index, supports fast searching. However, due to the growing popularity of the write-intensive workloads, people move to LSM tree as the new type of database index schema. LSM tree does auto-place update, which means when update the value of a key, instead of updating it directly, insert it as a new key value pair, and remove the old value later. LSM tree buffers the write in memory first, sorts by key, and then flashes the memory component to the disk with sequential I/O. Therefore, it has high write throughput. It's a popular index schema in both academia and industry. Here are several open source and commercial databases use LSM tree. In the disk, LSM tree has level-by-level structure. Each level stores a set of disk components. The disk components can be SS table, B tree, or R tree depends on the applications. Overall, there are two types of LSM trees, tiered LSM tree in Figure 2 and leveled LSM tree in Figure 3. Level 0 is in memory, the rest are on disk. On disk, each level is t times larger than the previous level. T is the size ratio. Tiered LSM tree has high write performance. Leveled LSM tree needs components in each level disjoint with each other. Therefore, when a new component flashes from upper level, it triggers a series of read-write operations to sort the new components with existing components in this level and build new disjoint components. In leveled LSM tree, each key only has one version in every level. It has better read performance than the tiered LSM tree. Our work is to keep improving the read performance of the leveled LSM tree. In the real-world applications, usually workloads are mixed with read and write. LSM tree suffers several problems when it deals with a mixed workload. Let's see an example. It is also included in our paper. If you want to read it carefully, please refer to our paper. There is a leveled LSM tree with 3 levels on disk. Each box represents a disk component. The number is the key range in each component. Consider a range query, searching from 30 to 50. The write components overlap with the range query. System will read them, open each write component, read several pages, sort the records in memory, and return the valid query answer to the user. Figure B shows the key of the records in each component. The number represents key. Update records are marked with apostrophe. For example, we found 45 in level 1 and 45 in level 3. Because level 1's 45 is an update, we will return its value in the query answer and ignore level 3's 45. Please notice, these components are stored on disk, require disk I/O to read them. In our example, we assume one disk I/O reads 5 records. Therefore, we might read records which are not in the query range, like 100 in level 1. There are 3 main problems here. First, the data spread out in many levels, which introduce lots of random read during the sort process. Also, lots of useless content like old version of the records not in the query range. All these problems hurt the read performance of the LSM tree. A directly solution is to do compaction. People also call this process merging. It organizes the record into sorted order, remove obsoletes. If we merge all the disk components together, generate a set of disjoint components, then the previous problems are solved. However, merging all the components is expensive. It needs to read everything, sort them, and rewrite everything. Recall the applications use LSM tree. They are write-intensive workload, big data applications. Rewrite everything is not affordable. In our work, we are trying to solve these problems with an efficient solution. Our goal is to let LSM tree read few components to answer the query, and read components with disjoint key. Our solution is hinted by compaction. It stores the hot access data together. Remove the useless content in the hot range. For example, if there is a component contains 30 to 50 in the level 1, we can directly use this component to answer the range query, and avoid checking the other components in the rest levels. The early stop idea is also used when LSM tree answers the point query. When the tree gets the point query result in the top level, it will stop the searching and directly return, because the new version's records are always flashed to the top level and merged downward. To achieve our goal and solution, there are several challenges. How to define and detect the hot range, how to decide when to build the special components, how to maintain them in the mixed workload. Now let's introduce the details of our solution and see how we address the above challenges. We introduce bi-directional LSM tree, different with original LSM tree merging content from top to bottom, or tree selects the hot access data, merging them upward to the up levels. We will make a copy of the hot access data and store them in a special disk buffer. We call the special disk buffer as Sentinel components. It's a type of disk component, contains the latest version of the records versus any components built older than them. Therefore, like processing point query in the regular LSM tree, we can also achieve early stop when performing range query, which improves the read performance for the LSM tree. Figure 6 shows an example of the bi-directional LSM tree. The blue components are Sentinel components. If we perform the range query 30 to 50 again, now we only need to open and read the two blue Sentinel components, and avoid opening and reading other red components. To create Sentinel components, we introduce 4 tools. Bucket key range, which is the smallest union to build the Sentinel components. It means each Sentinel component is built based on one bucket range. A partition function to define the bucket range. Counters, which are used to accumulate the read and write cost in each bucket range. A cost function to evaluate when to build the Sentinel components for a bucket range. Next, let's look at more details. Due to the time limit, I cannot cover every technical details in the paper. If you are interested, please refer to our paper. There are lots of flexibility for the partition functions. We can use the linear partition function to uniform partition the whole key range, like the example in Figure 7. If we can get samples of the workload, we can build histogram to know the key distribution, have non-uniform partition function. Simply speaking, the partition function should return the indexes of the bucket range for the given key range. Now let's see counters and the cost function. For each bucket range, we use a read counter and a write counter to keep track how many disk IOs happen in this range. Here is the cost function. It estimates the benefit if building Sentinel components. The benefit is the potential saved future disk IOs take to store the query answer. The benefit is the difference between the number of pages actual read and the number of pages to store the query answer. We assume the data workload is similar within several adjacent time windows. Therefore, we can use the existing benefit to estimate the future benefit before the next flash happens. FW total is the number of pages that can be filled in the memory component before the next flash happens. When we found the estimated future benefit is larger than the write cost of building the Sentinel component, we build it. Now let's see the experiment result. Here is the test platform. Here are the experiment settings. We compared bi-directional LSM tree with leveled LSM tree, because the leveled LSM tree has better read performance than the tiered LSM tree. We test with read-only workload, mixed workload. We test with workload that contains the hot range and does not contain the hot range, contains obsolete and does not contain. This table shows the I/O cost comparisons. We compute the overall disk I/Os to perform each workload, and compute how much difference between the leveled LSM tree and the bidirectional LSM tree. Overall, there are 8 different workloads. Bidirectional LSM tree almost beat the leveled LSM tree in every workload. The last column shows how many Sentinel components that the bidirectional LSM tree built. The total cost also includes the building cost of Sentinel component. Overall, we found when there are hot access range in the workload, bidirectional LSM tree can save more than 10% of disk I/O than the leveled LSM tree. Improving read performance of LSM tree is a hot topic in the research community. Here list several works published recently. Every work improved the read performance from different directions, like building extra index, optimizing bloom filter, having extra disk buffer, delaying hot records compaction. It's a hot and interesting topic to work on. In summary, we proposed the bi-directional LSM tree to improve the read performance for LSM tree by following: detect the hot access range, store them with sequential I/O, and merge them upward to the tree. There are still several future directions can keep working on, like auto-turned partition function, also taking care of the hot range from write operations. Thanks to the NFF grant to support us finish this work. Here are the related work mentioned in this presentation. Thanks for everyone to watch the presentation. If you have any question, feel free to contact us by email.